Hello and welcome. Today we're going to be talking about heat conduction in one dimension. So the basic idea today, the big theme, is two things. One is express so we'll call this number one, express heat conduction or conduction in terms of a conservation principle. And specifically, this will be a mathematical expression. One that we're going to use over and over again as we study lots of different equations. But right now we're going to do it for heat. And two, the other thing that's going to be used is we're going to combine with our conservation principle some physical laws. So in particular, how we can actually incorporate a physical law into our conservation principle. So the particular law will be about heat transfer. Okay, so what I mean here is that heat transfer itself isn't a mathematical law that we can just derive from first principles, but something we have to take as an assumption about how the physical world works. And when we take that assumption and combine it with our conservation principle, together what we're going to get out of both of these things is something called the heat equation. So let's get started. So we're talking about a 1D object. So we're going to express this as a rod, and it's got a little area there, A, and it goes all the way over to here. We can express it as that. Also A there, and it's going from x is equal to 0 all the way to x is equal to L. It's got some length to it. And likewise, what we're going to do is we're going to assume how does heat transfer. It can only, so we're going to assume heat energy only moves in the x direction. So what we mean by that is we're going to put like a perfect insulator around this rod. And we're going to put the same insulation on the bottom there. Okay, and the idea here is then we can have some heat transfer going side to side, but nothing else. So this will truly be in one dimension. Okay, so with that, then we have to label some variables. The first thing we're going to talk about is a thermal energy density. So the textbook uses this notation, so they call E of x comma t is a thermal energy density. Okay, so a thermal energy density, and what do we mean by thermal energy? All right, so let's get this straight. So this material, we're going to think of this rod, right? And we'll just for the purpose of making things concrete, we'll assume it's made out of metal, and metal is we can think of it as having a bunch of atoms, a bunch of molecules connected by chemical bonds, say. And so those chemical bonds, of course, if there's thermal energy in this material, we expect these atoms to vibrate back and forth. like such. And they could go up and down, right and left, and so on and so forth. But they also have chemical bonds, which sort of act like springs. So we can think of that there's both kinetic energy but there's also potential energy as well. And the potential energy comes when one atom goes that way and the other atom goes that way. The chemical bond gets strained and it's pulling them back, and that strain of the spring, of course, is storing energy, which then causes the molecules to vibrate back and forth. So we have these two ideas. And then we have some notion of heat transfer. So if we look to a neighboring atom, if we look at these neighboring atoms in the lattice, if you will, if there's vibration on this atom right there, it's going to be stretching the spring, the chemical bond between, to this atom, and eventually it's going to be imparting some of energy to its neighbors laterally, and also across everywhere there's a connection, and that of course is going to keep propagating this sort of vibration throughout the medium. And that's the idea, is that eventually all the energy is going to spread out. And so that's generally the nature of what we think about when we think about heat conduction, like that. So so energy in this case is going to be at a microscopic scale. It's going to be composed of kinetic energy and this potential energy between chemical bonds. But at the macroscopic level, we have some way of just representing all of the thermal energy out of all of those molecules at the microscopic level. We'll say that there is some way of measuring all of that energy, and we'll call that the thermal energy density, and that will be energy per unit mass. Okay, so I'm sorry, I didn't mean per unit mass. I'm going to say per unit volume. Okay, energy per unit volume, and I'll put that, the units like that as such. Okay, so if I want to find the total energy in some region, so if I say I want to go from here to here, I'm going to call that x is equal to A and x is equal to B right there. And now I want to find the total energy in that whole region. What I can do is I can do this as follows. I say that H will be the total from A to B, and that'll be the total energy, which we'll call the heat energy, and that's going to be the integral from A to B of E x comma t dx. All right, but then we need to do one more thing, which is to multiply it by the area there, right? Because dx times an area, that gives the total energy over a volume, right? Okay, so there's our expression of the total energy. And what we want to do now is talk about what are the ways that which energy can enter and leave this region here, from here to here. All right, so two things can happen. So we say that what we want to do now is express dynamics of H tot. All right, and so that by that we mean the derivative of H tot over time. All right, so we want to know what's this going to be, and we know this has to be equal to one. There either one of two things can happen that can create energy inside of this region from A all the way to B. One thing you can get transfer of energy, so energy transfer. Energy transfer from the boundaries. Okay, plus another kind of energy that could happen is endogenously created energy. Or for that matter, destruction. So when we're thinking here, when we said their energy transfer, we could have energy leaving the system or coming in, or we could have energy being created inside this little region here, or we could have destruction. Either one's possible. So an example of this is some sort of chemical reaction. In general, though, I'm not going to consider this any further. I'm going to only assume energy is coming from the boundaries, that we have no chemical reactions, that all of our chemical reactions have died off and now they're in equilibrium, and so we have no more any energy from any other way of getting in except for from the boundaries. So we'll just assume that. So from this, we have to describe another quantity. So we have our H tote, we have our thermal energy. We have to describe one more quantity, and that is that of flux. And I'm going to give that label a phi of x comma t, and it represents energy transfer per unit area per unit time. Okay, and so we can represent phi sort of as an arrow. So that in this case will be phi of A. We'll just consider time to be frozen for now. Phi of A, and the length of phi of A indicates how much energy is coming in, and then we'll have phi of B be there. Okay, and notice that energy transfer, so basically what we mean here is that what we have to describe here is that a positive phi means transfer from the left to right. And if phi is less than 0, that would mean the energy transfer, the arrow is going the other direction. Okay, straightforward enough to make that expression. So of course on the balance then, if there's if dH tote dt, it's going to have to be the difference between those two fluxes, right? So it's going to have to be what's coming in minus, hold on one second, comma t minus what's leaving. That's good enough. All right, so I can rewrite this. And remember that h tote is this integral right here. I'm going to give myself a little room here and just erase that for a second and just make it go up a little higher so I can give myself enough runway here. Oops. There we go. All right, so this, recall, if I want to rewrite this, this is going to be the derivative over time, and I'm going to replace h tote with this integral here, which is going to be a to b e of x comma t dx times a. All right, so I forgot one thing here. Because this was energy per unit area, we have to multiply an area by here. Okay, fine enough as it is. So now here's a tricky part. So we have this derivative, this time derivative, and we want to bring it inside, but this is a sticky issue mathematically to do this. We have to make sure one thing, which is this only works. We can bring this derivative inside only when we assume that this is smooth. So assuming that is true, and in most realistic physical situations, this is certainly true. So we go from a to b, and then when we move it inside the integral, this time derivative becomes a partial differential as such. And now what we have here is, if we're looking at this, this looks like something like the fundamental theorem of calculus. So again, we have to make sure to put that A there. And we can express that as such as well. We have an A, integral from A to B, which is equal to the negative partial of the flux with respect to x. All right, so now under the integral sign, we see that we have one partial derivative in time and another partial derivative in space, and one is the thermal energy density, and here is the flux of thermal energy per unit area per unit time, all inside of the integrals. So what I'm going to do is, we need to get a new sheet of paper, and I'm going to just write our basic situation down again. A to B. We have our phi A and our phi B there. And what we've derived here is, with the A's hanging out front, A to B, partial of E with respect to t dx is equal to A times the partial of A with respect to B of the negative flux derivative with respect to x dx. All right, so this is true for any AB interval in the rod. So it should be true outside of the integral. So we can write down this equation here. All right, so we're almost there. We have this thermal energy density, and now we have what looks like two quantities, the thermal energy and this energy flux. All right, so now we need to do a bit of physics. So this right here, again, is a conservation principle. It says, again, the change in time of the energy density inside this region here is going to be, provided A is, we can make, it's true for any interval, so it can be true for very, very small intervals, for A getting closer and closer to B. Then it's true then that it has to be the change in the flux over space. Okay, and that is, again, the difference of flux from here to there, which gives on the balance how much heat is entering or leaving the system. And we have a negative sign to make the principle work. So that's our conservation principle. The growth or decay of the interior equals the difference of what's leaving and what's entering on the boundary. Okay, so that's our conservation principle. The next we need to do some physics in order to, so that's our number one of our goals. The two is going to be doing some physics. Maybe I'll write that down here. We have to do some physics. First is thermal energy density. That's hard to measure. How exactly do we do that? So what we mean there is that all those chemical bonds, all of the vibration of all the atoms, all of that is a microscopic stuff that we can't really get an estimate of. But what we do measure is actually temperature. So what we need to do is convert E to temperature. And what I mean is, we'll call that U of x comma t, which will be the temperature. All right, so how do we do that? Well, recall that energy and temperature are related through a complicated property. It depends. So I should say E and U i.e. the energy and the temperature depend they depend on material properties. So what are those material properties? Well, what we call the specific heat. C, and that's our new variable, is the specific heat. And we can make it a function of x if our material changes over space, is the specific heat. And we should say also that U is the temperature per unit mass. And specific heat is going to be the amount of energy that it takes to raise the temperature of a mass a given degree. So that's the units of the specific heat. It's the amount of energy per unit mass that will raise the temperature per unit temperature. What we mean here is that, and I need to back up and be careful here. What I mean is that if a given mass described by U raises in 1 degree of temperature, then it will raise the energy by a fixed amount. So that's our units for our specific heat. And then we also define the mass density, which could also vary over this spatial extent, right? So we could have a more dense area here and a less dense area there. So all of these things are important, and we can imagine some physical situations where the mass density may vary. If this were a heat sink or some sort of cooling rod connected to some sort of a device that needs to let off heat, we may have it more massive at the base of it and less massive at the end, and all sorts of things like that. And the specific heat may change if it's a composite material which contains a blend of materials that varies over space. So you can imagine there can be changes to all those things. So what we write down then is, for the bar, if we have E is that thermal energy density, and we times it by, we're going to do it for a very small little window of space, which we'll call delta x. We can say that H tot is approximately equal to the thermal energy density times the area times delta x. And that's going to be equal to the specific heat, which is a material property of our rod, times the mass density of our rod, times the temperature per unit mass, which is our new variable that we've defined here, times our volume of our little tiny wedge right there. All right, so here we go. And now, of course, we can rewrite our system again. So we had before this equation, and now because this was only a derivative in time, we can change variables to u, and now write the following statement. Our specific heat times the mass density is equal to u partial of T is equal to the negative partial of our heat flux, just like before. Okay, so now we've changed variables on this left side. We're no longer talking about thermal energy density, we're talking about temperature. Temperature is something we can imagine we could measure a lot more readily with a thermometer across this thing. So again, these are just a lot of notational details here. they're tough to get through, but I promise you this is going to be useful later on. So the next thing we need to do is talk about this heat flux. What exactly is this? So this is where our physics comes in again, and we're going to have to go to a new sheet of paper. All right, so again we have our specific heat times our mass density is equal to U, the time derivative of our temperature, which is equal to the negative derivative of phi of x. So what we need to do is, we want to define what this flux is. What's the rule? So, and this is where we incorporate a physical law. So flux, we say flux is determined by a physical law. The particular law that it's determined by is given. It was given by Fourier. It's Fourier's law. Okay, so what is this law? We'll write down a few bullet points that are important. One is, and this is all done. This was initially postulated through observation. So one is that we can write this down, that if the first principle here of the law is if U is constant, in a spatial region, then we expect the flux to be 0, right? And that means that the partial of U with respect to t will also be 0, because if the time derivative or the spatial derivative of flux, if the flux is 0, then the spatial derivative of flux is also 0, which makes no change in heat happen. So we can think of constant temperature throughout the entire spatial region as being an equilibrium point. Okay, so another part of the law. So we have to postulate this. If U at some point A, and we'll just think of time as being frozen, is less than U at some point B, where we think again on the rod, that's A there, and there's B. If this is true, then we would say that the flux is going to be less than 0. Likewise, if U of A is bigger than U of B, we would say that the flux is going to be positive. And this is just saying that energy flows from hot to cold. That's the that is the word description of this statement here. Okay, and so the final thing is that the flux rate, the flux magnitude depends on material. So one convenient way to write this all out, so you could think of many functional forms that F could take on. But the most simple, parsimonious one would be that would be that of the negative derivative of temperature over space times some constant. This constant we're going to call the thermal conductivity. So thermal conductivity, and again, this is a material property. All right, and this again is the negative spatial derivative. So let's just check to make sure this works. Again, if I said that if u of A is less than u of B, then that would imply that the partial of u with respect to x, as long as A and B are close enough together, we know that this has to be true, that this is going to be a positive slope, right? We're going to have u going up as we go that way. So this would be a positive number, and we think of this thermal conductivity, we'll assume that it's a positive number as well. So that means that the flux is going to be negative, which is precisely what we expressed there. Likewise, if we have a declining temperature over the region from A to B, then we'd expect that the flux will be negative. All right, and so this magnitude depends on the material. That's just, again, another material constant that we take with us in our equation. So now what we've done is we've expressed flux, this notion of flux, which we didn't really define. We've actually applied a physical law. This applies a physical law. What I mean is, by setting these two equal, we're asserting a physical law that governs the flux of heat in a system. All right, so we can write this all down. So now we have phi is equal to negative k0, the spatial derivative of u, and then we also have this expression, material property of the specific heat, the mass density, the partial of u with respect to t, and that's equal to the negative partial derivative of the flux with respect to x. All right, so this is what we call Fourier's law. And here, we call this the continuity equation. So the continuity equation says that, again, the temperature will change, and that's governed by the change in the flux over the spatial region. So the time derivative change of our temperature will change based on the change in flux spatially, and it's the negative change in flux. All right, so this is a mathematical principle. What I mean by mathematical principle is it's one of conservation. And why is it what I call this mathematical? Because conservation essentially says that it all has to add up. That's the take-home message of a conservation principle. And of course, when we mean add up, we literally mean mathematically. It's all accounted for. Nothing disappears. Fourier's law, then, again, is a physical assertion. This comes from experiment. This comes from hypothesis testing. This is an approximation of reality, but it's a very good one for most systems macroscopically, that our heat flux depends on the negative spatial derivative. So we combine these two things together, and we get specific heat, mass density, the partial derivative of u with respect to t, and that's equal to the negative derivative. I'm going to put this in brackets here, and we would put the flux being, but now we're going to apply our Fourier's law, put that in there, and we're going to have that, again, the negative k0 like that. And now we'll assume that for now, if this could be a function of x, again, that material could change over space. We could write that as a function of x, and we leave it as this. But now, for this point, for simplicity, we'll say that C rho and K0 are constants. That is, we have a uniform rod. Okay. Then putting this all together, we get partial of u with respect to t. And because this k is a constant, it can go through the derivative. We have a negative and a negative sign, which makes it positive, and we get a capital K over 0 all over c times rho times the second, so we have a first derivative and another derivative there, so that becomes a second spatial derivative in x, and we can rewrite this constant here we'll say is, we'll call that little k, so we call this, and I'll just write that in the most compact form possible, we call this the heat equation. Again, it is a combination of a physical law that we assert and an accounting principle or a conservation principle that that comes from basic principles of that everything has to add up, that nothing disappears. Okay, so that creates the heat equation. So obviously this is just a more elaborate version of the heat equation as well, and that's where we have the conductivity changing over time, and then we also could have the specific heat changing over time and the mass density changing over time. All of those, of course, then get rolled up into this parameter here, which we call K, and we call this parameter, we give it another name, we call it the thermal diffusivity. All right, so that gives us, so here's the heat equation for a uniform rod right here, and there is the more general version for a non-uniform rod. But what we're going to do in the next few lectures, in the next few days, is study this equation and study some of its properties. And this is our first idea, this is the first presentation of what we call a partial differential equation. All right, so thank you very much.